Hey guys, so in this video I want to talk about the angular momentum, L, of a point mass. Now remember that in rotational problems we can have either a point mass, which is a tiny object of no shape, of no radius, no volume, or you can have a rigid body, an extended body, which is an object of a known shape that has a radius, has a volume. And depending on whether you have a point mass or a rigid body, questions are going to be a little bit different. So let's look at the angular momentum of a point mass. Let's check it out. So first, I want to talk about a point mass in a circular path. A point mass, tiny little m, in a circular path like this, about a central axis right there. It's going to have a rotational speed, omega, and it has a linear equivalence, v10. v10 is a tangential velocity that you have when you're spinning. Now, this does not mean that you have two types of motions. You only have one type of motion, which is rotational motion. Okay? Just because you have a W and a V, it doesn't mean that you have linear and angular motion. You only have rotational motion. That's why I called this a linear equivalence. Okay? So that's the first distinction I want to make. I also want to point out that linear momentum and rotational momentum are not going to give you the same number. So because I have an omega, I can find a rotational momentum. Rotational momentum, L equals I omega. So if I have omega, I have this. Well, if I'm going in a circle, I also have a equivalent velocity, v10. So because I have a v that's equivalent to the w, I can find a linear momentum as well. So if I have a w, I can calculate L. If I have a v, I can calculate P. But these two will not give you the same number. And that's because linear momentum, remember, is absolute, but angular momentum is relative. It depends on the axis. So P is always going to be the same if your v is the same. But if you change the radius of your rotation, your L will change. So these numbers will not be equivalent to each other. They'll not be the same number. Okay? If you calculate linear and angular momenta is just plural for momentum. Linear momentum is P, angular momentum is L. For a point mass, you're going to get different equations and different numbers. We're going to do a quick example here so I can show you what I mean by that, and you see how this stuff works. So I have a small 2 kilogram object, so mass equals 2. Small tells me that this is going to be a point mass. It's not going to have a shape. It spins horizontally around a vertical axis. So spinning horizontally means you spin like this. Around a vertical axis is just imagine that you have an imaginary line that you spin around that line. And that line is vertical. Okay? So I'm going to draw the axis here. And you're sort of spinning like this. Okay, so here's the object M right there. You do this at a rate of 3 radians per second. 3 radians per second is going to be your omega. You know that because of the units, radians per second, so omega equals 3. And it says maintaining a constant distance of 4 to the axis. So it means that your distance to the axis is going to be 4. Distance to the axis is little r, so I'm going to write that little r is 4. All right, so we want to know what is the object's linear momentum and what is the object's angular momentum about its central axis. So for A, we're looking for P equals mv, and then for B, we're looking for L equals I omega. Okay, now for the purposes of solving this question, before I find the numbers, I actually want to change up these equations. I can change L to make it look kind of like P, and I want to do this to show you that even though L can look like P, it's not going to be exactly the same. Okay, you'll see what I mean once I get there. So what I'm going to do here is I'm going to replace I with the moment of inertia equation. Remember, moment of inertia of a point mass is given by mr squared, where r is distance to the center, to the axis of rotation. So I'm going to rewrite this as mr squared. Now, omega is related to v, right? So if you're spinning like this, and you have an omega, and you have a v, they are related by, here's an r. Our vector is the length, the distance, right? They're related by v equals r omega. So if I rewrite omega, omega is going to be v over r. Okay, so instead of omega, I'm going to have v over r. Again, I'm doing this to show you something. Look what happens here. R cancels with r, and then I have mrv. I'm going to change that around, and I'm going to write instead of mvr. And the point that I want to make here is that P is mv, and L is mvr. Therefore, not the same equation and not the same number. Okay, so now we can plug stuff in. Mass is 2. The velocity would have to calculate that. So v equals rw. So r's distance 4, w is 3. So v is 12. So m is 2, and then this is 12. So this is going to be 24. And it's kilograms times meters per second. Now for L, I have mass, which is 2. I have 12 as the velocity, and r is the distance, which is 4. So this is going to be 96 kilograms times meters squared over seconds. Okay? So notice how these are different equations and they are different answers. Okay? The only case in which they will be the same is if the r happens to be 1, which is just a gigantic coincidence. And then in that case, they will happen to be the same, but there's nothing special about an r equals 1 other than you get the same numerical value. Okay, so that's it for this one. The last point I'm going to make here is that this equation that we got here, that L, so L is I omega, but you can also have L as mvr for a point mass. So this equation, L mvr, is also used for angular momentum, L, of an object in linear motion about an axis of rotation. So if you ever get asked a question that says, find the angular momentum of an object about an axis of rotation, this is how you would do it. Okay, we're going to do more of this soon, but I want to quickly show you an example. Let's say, this is one of the classic ones. Let's say you have this a bar being supported by a fulcrum here, and then a little object is falling here, right? So the object is about to hit. So when the object is about to hit, it has a velocity, let's say, of 10. Okay? So even though this object is moving in linear motion, you can ask, what is the angular momentum of this object relative to the axis of rotation? The axis of rotation is here, because this is the point about which this could spin. You would write that L is mvr. You would be given the m. V is 10, and r would be this distance here. Okay, so this equation here can be used if you want to find the angular momentum of an object that has linear motion. Okay, so that's it for this one. Hope this makes sense. Let me know if you have any questions, and let's keep going.